Hi. All right, now we're going to talk about wave motion. How do these things travel? First of all, it's very important to realize that waves transport energy and not matter. So you might not want to accept that at first, but it is true. So let's picture a nice quiet pond and you drop a stone in that pond. What happens is the ripples that you're maybe picturing in your mind right now are spread out, but they're not actually carrying water across the pond. And you may wish to argue with me. You may want to say, yes, I know that if I drop a big enough stone and it makes big enough ripples, that some of that water will splash out of the edge of the pond. And that may be true. But the water that splashes out of the edge is the water that was already at the edge of the pond. It's the water that was already there, like by the sand or the grass or whatever's there. The water, what's really happening is you drop that stone and the individual water molecules are like going up and down. So let's picture now waves traveling across the grass on a windy day. Those are waves too. You can see that wave motion if you have like really tall unmown grass or weeds, something like that. Those individual pieces of grass or weeds, whatever they are not moving from one place to another. They're staying there. They're anchored to the ground. What's happening is energy is moving. So in the air, you can't see them, but we know that they're there. We always talk about them being there. Molecules in the air propagate a disturbance through the air. And the one that we're most familiar with, and I'll keep using as an example, is sound. So right now, you may be listening to the dulcet tones of my voice. You might be listening to me. You might hear me. You may be not listening to me because this is a video. Maybe it's nice and quiet where you are and you've got the captions on. But if you're listening to me, what's happening is a speaker somewhere in your computer, however you're watching this, is moving. It's vibrating and it's moving the air molecules right next to it. And those air molecules then move the air molecules right next to them. And then those air molecules move the air molecules right next to them. So here's our speaker, and it's shaking. The speaker, I'm moving all around, I'm vibrating. Okay, so there's air molecules here. So they start moving, and there's air molecules right here next to them. They start moving, and there's air molecules right next to them. So they start moving. And there's air molecules right next to those air molecules, and I think you see where this is going at this point. They start moving all the way to your ear. So the air molecules right next to your eardrum, right next to your tympanic membrane start moving, and that is how you hear. It's the propagation of those sound waves. It's an ear, trust me. So it's not that when I talk and we're in the same room, or when the speaker vibrates to make noise, it's not that it's sending those air molecules that are right next to it to your eardrum to hit it. It is just bumping air molecules, which bump the air molecules right next to them, which bump the air molecules right next to them, all the way to your ear. Okay. Let's look at the next slide. So let's say you have a nice big bowl of water, like the biggest mixing bowl you can find in your kitchen, or if you want to fill your bathtub, something like that. If you take a little thing that floats, and if you actually want to try this at home, I'd recommend you do it. Why not? Take a little thing that floats and put it on the surface of the water, and then take something heavy and drop it, like a rock or whatever. You drop it right into the middle of your big body of water. Be sure and clean up whatever mess you make. I don't want angry letters from roommates and parents and sisters and brothers. So you're going to drop a stone, and it's going to make the water ripple. Ideally, what you will see happen is you will see that little floating mass that you put in if you don't have anything you can think of that floats, like a little piece of cork, something like that, the small plastic cap from a water bottle, a disposable water bottle, works pretty well. So you will see that floating thing just move up and down. It's not going to go over to the edge. It's just going to move up and down. So those water molecules move up and down, and they transport energy, not matter. So what do we mean when we say wave speed? Wave speed is telling you how fast some disturbance is moving through a medium. So when I say a disturbance, when I'm talking and you can hear me, I have disturbed the air molecules. How fast is that disturbance moving? It's related to both frequency and the wavelength of a wave. So your wave speed, this is a very important equation. You're going to see it a lot. The wave speed is equal to the frequency times the wavelength. And that's what I've written out here. We're using V for velocity or speed, right? F for frequency, and then lambda, you know, is meaning wavelength. It's lambda, again. I don't know how long ago you watched the first video, and that's the wavelength. So for example, if you have a wave with a wavelength of 1 meter and it has a frequency of 1 hertz, it has a speed of 1 meter per second. So let's picture this little bird. He's right here. He's at the crest of this wave. In 1 meter of space, that next crest is going to get to him. And if it's moving at 1 meter per second, that's going to happen in 1 second. So the greater your wavelength, you can see here I have a pretty, oh no, I erased half my little guy. I have a pretty long wavelength there. Here I have a nice tight wavelength down at the bottom. Smaller wavelength is greater frequency. Smaller wavelength means greater frequency, just like the guy we talked about before. All right, let's look at this. Say I have a wavelength of 10 meters in a wave. Time in between crests is 0.5 seconds. Time in between crests is 0.5 seconds. That's telling us something important. And it's traveling in the water. I want to know, what is the wave speed? Well, I know the wave speed is equal to the frequency times the wavelength. So the wave speed, if the time in between crests is 0.5 seconds, it's a half a second from crest to crest, what is the frequency, is what I want to know. So you might be tempted to put in 0.5 seconds for the frequency, but remember that frequency is cycles per second. That is telling you the period. So 0.5 seconds, crest to crest is 0.5 seconds. That's telling you, that looks really messy. That's telling you the period of this wave, okay? Crest to crest is 0.5 seconds. So if the period is 0.5 seconds, that means the frequency is 1 over 0.5 seconds. So it's 2 hertz. That means it's completing 2 cycles every 1 second, because it takes half a second to complete 1 cycle. All right, so now I can see the frequency is 2 hertz, or 2 cycles per second, and my wavelength is 10 meters. So my velocity is going to be 2 cycles per second times 10 meters, or 20 meters per second. Yay, there we go. All right, so it was a little trickier than maybe we thought, because it didn't just outright tell us the frequency, it told us the period, and from that we had to remember how to get the frequency. All right. The period of a pendulum is given by this equation. Do you have to know it? Yes, you do. So T is period, not time, is a measure of time. But specifically, it's the period of a pendulum. 2 is 2, pi is pi. And then we have the square root of the length divided by g, which is the acceleration due to gravity. So this is the length of this string, the length of your pendulum. And this is g wherever you are, whatever planet you're on. Usually we're on Earth. So 9.8 meters per second every second, provided we're here on Earth. For somewhere else, g is different. So let's talk about these transverse and longitudinal waves. And if I were together with you, I would be getting out some slinkies right now, but we can picture them. So the two common types of waves that we're going to talk about right now are transverse waves and longitudinal waves. So they're different in that the direction that the medium, so let's just talk about air molecules. That's the medium that carries sound waves. So the direction in which the medium is moving compared with the direction in which the wave is moving. So if I had a slinky, let's say I have a slinky, and I stretched it out, I pulled, and I got those slinky coils really far apart, and then I let it go. I pushed them this way. The medium that is making up that wave is actually slinky coils, and they are moving this way, right? And the wave is moving that way. Think about what way is the energy going? The energy is also going that way. So the thing that is making up the wave is moving parallel to the wave, so that is transverse. Ugh. Guys, that is longitudinal. I wish I knew how to edit this. Longitudinal. So the slinky coils are moving in the same direction as the wave. That's a longitudinal wave, longitudinal. If, however, I take my slinky and instead of doing that, instead of stretching those coils out and pushing them toward one end, I kind of just pull one end of the slinky down, then I get a wave that's moving like this. I'm moving it like this. So I am moving the slinky up and down. I'm shaking it. So the thing making up the wave is still slinky coils. But guys, the wave is still moving like from here to here. So if I'm moving the slinky over here at point A, the energy is starting here at me in my hand. I'm moving the slinky up and down, and it's going over here. Picture you're holding the other end of the slinky. So this time, that's the way the wave is moving, still along that way, but up and down is the direction that the medium, the slinky coils, are moving in. So that is a transverse wave. And slinky demo, maybe you can do at home if you have a slinky. I don't know. All right. So that wave that you start when you drop that stone in your bathtub or in your big, huge mixing bowl, if you have one, and you want to fill up your sink, something like that, that's a transverse wave because the water molecules are going up and down, but the direction of the wave is from the center out. So if you look at this red arrow, I'm saying the wave is starting here and it's going out this way, but at the same time that the water molecules are going like up and down. So they're moving in a direction that is perpendicular to the direction of wave travel. So the medium, if you drop that stone in the water, your medium is water molecules. That's what's making the wave. So medium moves perpendicular to direction of wave travel. You're like, oh, what is she talking about? These big math words. It just means at right angles too, perpendicular. All right. This is exactly what we just talked about. So a transverse wave, the medium is moving perpendicular to the direction of wave travel. So you can picture that stone that you drop in the water, or just picture me shaking a string, a jump rope, slinky, up and down, back and forth. I'm moving it. Another example is vibrations in the stretched strings of musical instruments. So if you have a guitar and you pluck that string, the string is moving back and forth. So the air molecules are moving back and forth, and it's traveling in a direction perpendicular to the direction that sound wave is traveling in. Another example is radio waves, light waves. We talk about these a lot. These are electromagnetic waves, and they all move at what we call the speed of light. I'm sure you've heard of the speed of light. And these are the ones that do not need a medium to travel in. You know, light doesn't need a medium to travel because there are no air molecules in space. But what gets here almost every day is sunlight. So the sun is shining, it's sending those light waves out, and they are traveling through space. There aren't any air molecules there to carry them. They still get to us, get to our atmosphere where we have air molecules. So the distance between adjacent peaks in the direction of travel for a transverse wave is what? Peak to peak, guys, we call what? What? Wavelength, yes, right, wavelength, nice. So the wavelength of a transverse wave is the distance between adjacent troughs or adjacent peaks, any identical spot to its next identical spot, but it's, like I said, easiest to just go peak to peak. So the vibrations along a transverse wave, which is what we just talked about, move in what direction? Along the wave, that's when I push the slinky coils. Perpendicular to the wave, that's when I shake the slinky. A and B, neither A nor B. So transverse, perpendicular. Can't write with an eraser. There you go. Longitudinal waves, the medium, if we're talking about sound waves, the medium is air molecules. Let's go ahead and write that down. For sound waves, the medium is air molecules. That's what carries them. So did you guys ever, you maybe are younger than me, I don't know, but there was a line from a movie and it was really famous, and it was, "In space, no one can hear you scream." And it was from, I think it was from the movie Alien. So if you like gross movies and you like horror movies, you've either seen this or you should see it if you like that kind of thing. But the line, "In space, no one can hear you scream," it's not because you're far away from Earth and that's why they can't hear you, or you're outside of the spaceship, no one can hear you because they're too far away. It's because in space, what do we not have? We don't have those air molecules. So if you and I get on a rocket ship together and we go up to the moon, and we're standing on the moon in our spacesuits, and then we get tired of the helmets and we decide to take them off, we take off our helmets, we can't talk to each other, even though we don't have helmets on, because there aren't any air molecules between us. There's nothing for me to vibrate with my vocal cords to reach your eardrum, to put pressure on your eardrum. So for sound waves, the medium is air molecules. And if they are not there, the wave is not going to travel. The medium for these longitudinal waves, the medium moves parallel to the direction of energy transfer. So backward and forward movement consists of compressions, where the medium is like bunched up, and rarefactions. So that's where it's spread out in between compressions. So the example we're going to use here is sound waves that are existing in a solid, a liquid, or a gas. So air is a gas. That's what we're most familiar with, sound waves moving through. Sound waves do move through solids, and they do move through liquids. So they move through liquids faster than they move through air, and they move through solids faster than they move through liquids, because those molecules are closer together in a solid. And here we have a good picture. So here, this is like a tube, and this is a tuning fork that is vibrating air molecules. I've hit the tuning fork, it's vibrating, so it's vibrating those air molecules. So these places where the air molecules are more tightly together, those are the compressions, where they're pressed up close to each other. And these areas here, where they're spread out, those are the rarefactions. And from compression to compression is going to be the wavelength of that sound wave that we're picturing right there. So the wavelength of a longitudinal wave, what do you think, is the distance between successive compression. Successive just means right next to each other. Successive rarefactions, both A or B, or neither A nor B. So neither A nor B doesn't make any sense. So it's got to be one of those. It's got to be A, B, or C. What do you think? Giving you time to make your guess. So it's going to be A and B. Remember, we can go from identical part to identical part. So we can go rarefaction to rarefaction, just like we can go compression to compression. Wave interference is what happens when two or more waves come into contact with each other. They're occurring in the same place at the same time. So the displacement due to the interference of those waves, we can figure out by adding the disturbances produced by each wave. So if you're right in time, if you're splashing, you're moving the water up and down in the pool or the lake, wherever you are, and your friend comes along and they're doing at the same time, they can either be against you and your waves run into each other and they're not so big, or they can be right in time with you and add, and then your waves are twice as big, right? So here is a cartoon picture of it. Constructive interference happens when these two things are happening at the same time. So this peak is happening at the same time and place as this peak, and this is what you will see. You won't see these two separately, you will just see this one. So you can see, you're meant to be able to see that peak is like twice as high as either the ones that's adding to make it, and that trough is twice as low as either the ones adding to make it. We can also have destructive interference, and that's what happens when the crest of one wave is happening at the same time as the very bottom, the trough of another. So what you will see is absolutamente nada. What you will see is nothing. But you will notice in both of those, it was either the exact peak adding to the exact peak, or it was the exact peak adding to the exact trough. So you can get a combination of effects as well. But for right now, I want you to concentrate on this and try to understand that. So here's an example of some light waves interfering, and you can look at these patterns. You have access to this video. You can look at it however long you want. But what you can see here is the interference pattern that is made up. This is actually not light waves. This is when two vibrating things, like for example, that tuning fork touch the surface of the water, and we're making water waves here. So the regions where crests are overlapping with trowels produce like no disturbance, like that really dark area you see there where everything is still. At other points, if we have a peak happening with the peak, you're going to get this really strong wave, like right there where it's the lightest. A standing wave, you can think about like this. If you took a rope and attached it to a wall somehow, and you were shaking the free end up and down, it wouldn't just have to be like a random pattern. At some point, you would fall into a standing wave. If you are shaking the free end up and down, you're making waves in the rope. The wall is not going to move. It's pretty hard. It would be impossible to move the wall with a rope, hopefully. So that wave is going to be that you send to the wall, from your hand to the wall, is going to be sent back to you, from the wall to your hand. So if you shake that rope just the right time for however long that rope is, you can get, when the standing wave comes, when the wave that you sent out comes back, you can get interference so that you create a standing wave. And that's what we have pictured right here. And this is one whole wavelength. So you see we're 0, way up to the top, 0 again, down to the bottom, back up to that 0 mid-level, and we would go up to the top there. So that is one whole wavelength that I've shown you right there. Let's try to neaten that up a little bit. Okay. And we call that a standing wave. So the area where it is having the most amount of movement, we call that, has a fancy science name, we call that the antinode. And here, where it doesn't move at all, we call that the node. So no displacement for node. And you know that however high it got from 0, that is its amplitude. So nodes are the reason, or the region where it doesn't move at all. So that's a node. This is our standing wave. It takes 2 loops to make one wavelength. 2 loops is one wavelength. Okay. Antinodes and nodes occur equally far apart from each other. And this is just an illustration again of a standing wave. So if we said from here to here is 5 meters, this would be your 2 loops. So your wavelength would be 5 meters. If you change how you're vibrating that, that string that is making that wave, or a piece of rope that's making that wave, you're going to change the wavelength because you're changing the frequency. So here I can see that that is a whole wave, but if that's still 5 meters, you would have to perform this little mathematical operation to solve for your wavelength. So it's not going to be exactly that 5 meters anymore. Another example of a standing wave happens when we talk about musical instruments. So if you were to say play the trumpet, like this guy, I think that's Dizzy Gillespie. If you were to play the trumpet, you are creating a standing wave like in the air column there in the instrument. The same thing with your guitar. I don't know if that's a famous guy or not, but you can see he's playing his guitar. So this string, this is a guitar string, goes back and forth, and then that makes a standing wave. And then I want to talk about the Doppler effect. So let's save that for next time, actually.